Hello students, so we are now in chapter 7 and in this chapter we are going to learn about thermodynamics. So this is the content for the whole chapter and we are going to cover the first two here, which are the thermal equilibrium and zeroth law of thermodynamics, as well as the first law of thermodynamics. So by the end of the lecture for these two subtopics, students are expected to be able to define and find solution to the general problems related to these two subtopics. Okay, so let us start our lesson. Okay, so in studying thermodynamics, there are certain important definitions and concepts that we need to learn. The first one is we must be able to differentiate between these two, the heat and temperature. Heat and temperature are related to each other, but these are two different concepts. Okay, so let us look at the following example. Let's say we have a solid matter here. So if we look deeper on the molecular level, we will see the particles. The particles in the solid have very little space between them, so they are not moving past each other. However, they are vibrating in their place, like this. So this vibration, the vibrations of the particles, is related to their kinetic energy. Okay, so what we have here is the kinetic energy of the particles. For example, we have Ke1 for particle 1, 2 for particle 2, and 3 for particle 3, and so on. So the total of this kinetic energy actually is what we call as heat. So in general, heat basically is the total energy of molecular motion in a substance. So the SI unit for heat is joule, J here. So on the other hand, not all of the particles here actually have the same kinetic energy. Instead, the particles may display a wide range of kinetic energies. Depending on the situation, some particles may have bigger kinetic energy than some other particles. So how do we quantify the kinetic energy? By introducing the temperature concept. So temperature in general is used to quantify the kinetic energy of the solid in average here. So we can define temperature as a measure of the average energy of molecular motion in a substance. So the SI unit for temperature is Kelvin. Okay. So in our daily life, we usually use the term temperature to represent the level of hotness or coldness of something with numbers. Okay, so the next concept is the internal energy U. So internal energy of a system is the energy contained within the system. So for a single atom, look here, the internal energy is derived from the motion alone. So in this case, the internal energy is purely kinetic. So beyond single atom, however, other than the kinetic energy due to the molecular motion here, there are also a molecular potential energy due to the intramolecular bonding. So the internal energy for the system now is given by the sum of the kinetic energy and then the sum of the potential energy. Okay, so next concept is about work. So naturally, heat flows from an object at a higher temperature to an object at lower temperature, and heat doesn't flow in the opposite direction. So this will continue until both of the objects have the same temperature here. Okay, so we can, however, force heat to flow in the opposite directions here from a lower temperature to higher temperature region by involving some work in the process. So in this chapter, we are going to refer work as the transfer of energy by mechanical means. So based on these four concepts, we basically can define thermodynamics as the study of heat and temperature and their relation to energy and work. Alright, so our next lesson is about the law of thermodynamics. Okay, so the first one is the zeroth law. There are four basically, and the first one is zeroth law. And then the zeroth law of thermodynamics is basically about thermal equilibriums, a situation where two systems have the same temperature and there is no heat flows within the two systems. Okay, so the zeroth law of thermodynamics says that if system A is in thermal equilibriums with system B, and system B is also in thermal equilibriums with system C, then system A and system C are also in thermal equilibriums. The zeroth law is important for the reason that it allows us to define the concept of a temperature scale. Okay, so we proceed our lesson by looking at the first law of thermodynamics. The first law of thermodynamics is a thermodynamics version of the law of conservation of energy. So before we go further, let us first look at the relationship between the internal energy, heat, and work in a system. Okay, so let's say we have a system here. So the change in the internal energy of this system depends on two things. the heat, and then the work. So let's say this is the first law of thermodynamics, and then we can also put the equation relating these three in general from in this form. So this is in general form. So depending on the situation, we will change the sign to get the final equations for this one. Okay, so look at. Okay, you have to remember this. So if we add heat on the system, okay, so let's say this is our system and this is the internal energy. So if we add heat on the system, the internal energy of the system will increase because we have additional heat. So plus Q. So on the other hand, if we remove heat from the system, the internal energy of the system will decrease because the system is losing heat. So negative Q. So if work is done on the system, the internal energy of the system will increase because energy is being transferred to the system. So plus W. On the other hand, if work is done by the system, the internal energy of the system will decrease. Why? Because the system is doing work, so it is losing energy. So negative W. So we have 4 different situations here. So depends on the situation, we can just directly formulate the equations for change in internal energy. So for example, okay, so for the first case, for heat is lost and work is done on by the system. Work is done by the system. So we have change of U equal to negative Q minus W. Okay, so for heat is lost, negative, and work is done on the system, we have change of U equal to negative Q plus W. For heat is added on the system, so Q plus, and work is done on the system, by the system, sorry, so we have change of U equal Q minus W. And lastly, for heat is added and work is done on the system, we have change of U equal to Q plus W. Okay, so please note that here the sign for both of the heat and work, the plus and minus, we are referring the sign to whether energy is being added or removed from the system. If we look at the lecture notes, however, the first law of thermodynamics is given in this following form. Notice the negative sign here. So if we are using this, there are some modifications on how we describe the work before. Heat added and loss are similar to the previous descriptions, plus and minus here. The sign is referring to whether heat is added or removed from the system. Heat in positive, heat out negative. However, for work done on the system now is become negative, and work done by the system now become positive. Okay, so now is the thing is, if work is done on the system, the internal energy of the system will increase because energy is being transferred to the system. Since we are adding energy, isn't work is supposed to be positive in this case? Okay, so for me, I like to think that these negative and positive signs here of the work here are not here to refer to whether energy is being added or not. However, it can be we can thought this as being an indication to whether work has been done or not done by the system. Okay, so for example, work done by the system. So work is positive because there is work being done by the system. So for work done on the system, work is done on the system. So the system is not doing any work. So work is negative for the system. Okay, so don't get confused. Doesn't matter which one we are going to use, we eventually will obtain the same final equation.